right. Well, Aziz, thank you so much for doing this. I am very, very pleased to introduce a relatively new faculty member to UAB, Dr. Aziz Ahmed. He's an assistant professor in the Department of Health Services Administration, and he is an informaticist. I think that's the right word. He comes to us actually from the University of Minnesota, Croxton, and he joined UAB, I guess, sometime this summer. And he is an industrial engineer. He received his PhD in industrial and systems engineering from the State University of New York in Binghamton. He also teaches in our graduate programs in health informatics, and he focuses a lot of his work and teaching activities on machine learning, the applications of novel optimization and machine learning techniques in the very, very complex healthcare environment. Without further ado, Aziz, take it away.
Good afternoon, everyone. Thank you, Alison, for the introduction. So today I will present a project that I did in the past about the applications of predictive and prescriptive analytics in the interpreting industry. Just to give you a context or background, analytics is just using data to make decision or to make data-driven decision. And analytics involves wide variety of methods and techniques. So it's not just counting and roll checking and basic arithmetics. So there are different levels of analytics. So we start with descriptive analytics, where as it implies, it describes the data like taking the mean, the average, standard deviation, all those basic statistics. And then the second level is the predictive analytics, where we use historical data to predict the future so we can react based on the predictive analytics result. And then the highest level of analytics is called prescriptive analytics, which is the core of today's topic. Prescriptive analytics is just using the input from predictive analytics, and then what happened after that? We need to optimize system and then make decision based on the predictive analytics. And then to give you a context, predictive analytics application, there are a lot of application and they're very clear. For example, predicting the stock market or cancer detection, or in healthcare operation, for example, predicting a patient will be admitted or discharged based on vital signs. So the application of predictive analytics is clear and very common. But prescriptive analytics, give you an example, because it's the main topic for the presentation, VRP problem or vehicle routing problem. So you have everybody drinks coffee in the morning from Starbucks, let's say. Starbucks has in every city, they have a hub or major inventory, and then they have many stores in a city like Birmingham or Chicago. And then in the morning, 6 a.m. or 5 a.m., there are lots of trucks departing the hub or the main inventory and then driving throughout the city to reach the stores or the coffee shops of Starbucks to supply them with different things like coffee and milk and et cetera, et cetera. So to optimize the routing of these trucks is called prescriptive analytics. So we can use historical data, or we can use stochastic optimization to optimize the routes of these trucks, because there is no single route. There are lots of routes, and taking different routes leads to different times and energy and cost and et cetera, et cetera. So optimizing these routes is called prescriptive analytics. In healthcare, there are a lot of applications of prescriptive analytics. One common problem is operating room scheduling, or bid assignment problem, or capacity optimization. So there are a lot of applications of prescriptive analytics in healthcare. Our application today is interpreter scheduling. So as I mentioned, the project, I did this in the past at UMN. The motivation of the project is that you can imagine there are 47 million people in the US, which is 18% of the population, speak language other than English at home. And 35 million of those 47 are foreign born. 11 million to 21 million people in the US considered as limited English proficiency patients, or either they cannot speak English or their English is very limited. In Minnesota, where this project was conducted, more than 80% of the population is comprised of immigrants, and they are located mainly in Minneapolis and St. Paul area. Also, one of the motivation is that according to the Civil Rights Act in 1964, delaying or denial of medical care due to language barrier is considered as a form of discrimination. And there are a lot of accreditation body or healthcare accreditation body that require interpreting services as necessary to acquire accreditation. In terms of service quality, when we compare the medical error and lots of measures like adhering to medications, and when we compare English-speaking patient and English proficiency patient, there are a lot of disparity there. So, for example, in 2005, one researcher collected more than 1,000 incidents over 7 months, and they found that 49% of the limited English proficiency patient experienced harm versus 29% of the English-speaking patient, and then 46% of the incidents ranged from moderate to temporary harm to death. So there are incidents that led to death due to language barrier, and then versus only 24% of the English-speaking patients. So, as I mentioned, this problem was conducted in this project is conducted in Minnesota, more specifically in North Memorial Hospital, which is close to Minneapolis. And then they have this interpreting department where they have full-time interpreter and part-time interpreters. And then full-time interpreters is only for like major language, like Hmong and Spanish and Russian and Vietnamese and Somalian. And then they have part-time interpreters where when the demand of the language exceeds the capacity of the full-time, they have to hire full-time, part-time interpreters. And then no fund is available. So you can imagine the cost of interpreting service could range from $30 to $400 per hour, while the Medicaid only reimburse from $30 to $50, and then private payers do not reimburse interpreting service. So this interpreting service is a cost drainage body in the hospital. So we need to optimize. We need to find a way to optimize the service. And as I mentioned, we have full-time interpreters and part-time interpreters. And then there are different patients. We have inpatient and outpatient and emergency patients. And then for part-time interpreter, they come from many agencies in Minneapolis. You can imagine Minneapolis, if you Google interpreting agency, you can find more than 30 or 40, or I think more than 100 interpreting agencies. So we need to recruit the best interpreters considering the cost and considering the quality of the service. So the goal is to develop a decision tool or an optimization model that we can use to assign full-time interpreter and part-time interpreter. At the same time, we need to minimize the cost, maximize the service quality, and we need to make sure that the demand is covered. And as I mentioned, we need to provide the highest quality of service to interpreters. So this is the framework of the study after collecting the data and defining the problem. We have two main phases. First phase is the predictive analytics or predictive model, where we predict the demand of the language at the emergency department, because as I mentioned, we have inpatient and outpatient and emergency patient. Inpatient and outpatient, their demand is known because they are scheduled ahead of time. But emergency patients are stochastic, so we need to predict it. And then after we collect the demand and we predict the demand, collect the inpatient and outpatient demand, and then predict the emergency patient demand, we send this along with other data that we will see later on. We send them to a multi-objective optimization model to find the optimal schedule for the interpreters. So as I mentioned, stage one is the predictive model to predict the hourly patient demand at the emergency patient, and then the prescriptive model, second phase, which is developing an optimization model that can be used to optimize the assignment of full-time and part-time interpreters. So this predictive model, since the demand at the emergency department is a time series data, so we need to use historical data. So for example, we can use the past 4 hours or 5 hours or 10 hours to predict the next demand, the next hour, or maybe the past 24 hours to predict the next 3 or 4 hours. So that's called lag. So we need to use the historical lag to predict the next, and it can be formulated as this matrix. And then we use the random forest, where I will not explain the random forest algorithm, but it's a predictive model that can be used to predict for classification and regression. So we consider this problem as a classification problem. And then we just perform typical predictive analytics procedure, which is dividing the data into training and testing, and do the training and do the testing and test the accuracy. And this is an iterative process until we get a high accuracy model. You can imagine here, if we plot the time, most of the time we don't have emergency patients who cannot speak English. So at some instance, we would have this patient who cannot speak English. So this data is imbalanced, and we treat it as a classification problem, which we take a specific hour. So every timestamp we see, whether we have patients or we don't. That's the Hmong language. And when, as I mentioned, we have other language. So since the data is imbalanced, we used oversampling smooth to mitigate the problem of imbalance. And then we prepare the data, we develop the model, and then we did the accuracy. So that's the methodology for the predictive model. And then now, after we predict the demand at the emergency patient, and then we develop the model for optimizing the assignment of full-time and part-time interpreter. And so we developed a mixed integer linear programming model. You can see here, these are the sets that we have. So we have full-time interpreters, we have part-time interpreters, and then we have patients, and we need to schedule them across the day, which is the timestamp. And then we have different input parameters, which are the hourly rate for the full-time, hourly rate for part-time, the availability of interpreters, the language match. So we need to assign Hmong interpreter to Hmong patient, and Spanish interpreter to Spanish patient, and so on and so forth. And then we have the demand at every timestamp. So we need to make sure that the demand is covered. And then how much the service time or the interpreting session. And then to evaluate the quality of interpreters, as I mentioned, the part-time interpreters come from a very large pool from many agencies. So we need to select the best interpreter, but at the same time to consider the cost. So it's multi-objective. So to model the quality, every company has a rating. It's like any store has a rating, Google rating. And then we use that rating to represent the quality of the part-time interpreters. And then of course we need to weigh between the total cost and the quality, and then we find the best combination. And then the main decision variables for the model is to assign full-time interpreter assign the right interpreter to the right patient at the right time for full-time, and then and then Y, J, and T is for part-time. So again, for full-time and part-time interpreters, we need to assign the right time, the right interpreter to the right patient at the right time, while minimizing the cost and maximizing the service quality, which is represented by the rating. And then we need to calculate from the model. There are measures that we need to calculate. For example, the total interpreting time for every interpreter, and then the completion time, so we can calculate the cost. So this is the mathematical model. I forgot to mention, part of the prescriptive analytics is to convert any system to a set of mathematical equations that represent the system. So here we're trying to represent this interpreting department or interpreting service in a set of equations so we can optimize the system. So this is the objective function. We need to minimize the total cost. The first part is the total cost for full-time, and then the second part is the total cost for the part-time interpreters. And then, as I mentioned, we need to represent the service quality, which is represented by the rating for part-time or agency interpreters. So we need to maximize this rating, because the higher the rating, the better service quality. And then the combination of both objective functions is weighted by alpha and beta. And then the second part of the mathematical model is called constraints. So we need to model the constraint of the system. So for example, the first three set of constraint is related to the relationship between interpreters and patients. So we need to make sure that the first one, for example, make sure that either a part-time interpreter or a full-time interpreter is assigned to a patient at the same time. So we cannot assign two interpreters at the same time. We need only one interpreter, and that interpreter is either a full-time interpreter or a part-time interpreter. So the summation of the interpreters should be less than or equal to 1. And then for every interpreter, we need to assign one patient. So we cannot assign two patients to the interpreter at the same time. So at every time step, every interpreter needs to work with only one patient, whether it's a full-time interpreter or a part-time interpreter, which is the Y. And then the second part, which is called interruption constraints, where once an interpreter starts working with a patient, that interpreter cannot be interrupted. So we call it interruption constraints. So we need the interpreter to stay with the patient until the interpreting session is finished. And that applies for both the full-time interpreter and part-time interpreter. And then we have the demand constraint, which means that we have to cover the demand. All the demand has to be covered. All the patient has to be covered throughout the day. We need to interpreter for the inpatient, outpatient, and emergency patient. All of them have to be covered by interpreters. And then another set of constraint is intended to model the language match. These two sets of constraints are the most important constraint in the model. So you can imagine that we cannot assign an interpreter who works with Russian language to a patient who speaks Spanish, or an interpreter who speaks Spanish to a patient who speak Hmong or Somalian. So we need to make sure that the language is matched. Every interpreter has to be assigned to the right patient. So we created a matrix that represents the language, and then we need to match this matrix with the assignment of interpreters. So whenever we assign those interpreter X's, which are the full-time interpreter, to a patient, they have to be matched. And then the same applies for the agency or part-time interpreters. And then at the same time, we need to consider the availability of both full-time and part-time, because we cannot assign an interpreter, a full-time interpreter, to a patient at the lunch break. So we need to consider also the availability of part-time interpreters and full-time interpreters. And then and then the same thing, also the availability, this called the total availability. And then once we, this also for the availability as well. So once we assign an interpreter to a patient, we cannot assign throughout the whole break. So the patient had the interpreter has to be idle the whole break. And then we calculate the total hours spent for interpreting all the interpreting sessions that are conducted by any interpreters, which is the total hour, so that we can calculate the total cost. And this applies for the full-time and part-time. And if we need to calculate the completion time, just to see when an interpreter is complete a session, so we can calculate the completion time as well. Those are measures that we can calculate from the mathematical model. And then, as I mentioned, in the objective function, if you remember, we have cost part, and then we have rating, and both of them, they have the different scales. So one in cost, and it could be in thousands and hundreds, and then we have this rating from 0 to 10. So they are in different scales, so we need to normalize them. So we did the normalization. And then to test the model, how this mathematical model works and does it work or not. So we conducted a numerical example to calculate or to develop a schedule over for 5 days. And then, so we collected the patient demand, as I mentioned, the surface time, the compatibility matrix, which is the match between the language and the interpreter, the language of patients and the language of interpreters. And then we have the hourly rate, how much an interpreter how much an interpreter is paid per hour, and the part-time interpreting rating, and then the availability. And those are some the availability metrics for the full-time. You can see we tested 5 languages: Hmong, Russian, Somalian, Vietnamese, and Spanish. And those are the most common language in Minneapolis, but the model can accommodate as many languages as we want. And those are other values of other parameters. And then this is the result of the predictive model. As I mentioned, we, after we trained the model and all of that, and we did the prediction. This is the prediction for the emergency patient, and then we combine that with the demand for the inpatient and outpatient, and then we run the optimization model. The ultimate output of the optimization model is this schedule. You can see for every interpreter we can have what interpreter and assign to what patient, and then the start and then the end. So that's the ultimate output of the model after combining the predictive model and the prescriptive model. So we can have a schedule that represent the assignment of any interpreter to any patient, what time start, and then the end. And then we compare the proposed model with the current system that they are using in the hospital. So what they're using is they don't consider the cost, and they don't consider the rating for the part-time interpreters. They just see what available interpreters full-time and part-time for a specific day, and then they used like something like Doodle or Google Calendar to book the interpreters, and then they do the schedule. So they don't consider any of the things that considers in this model. So we did a comparison. You can see here that we were able to save cost and increase the quality of the service, which was represented by the rating of the part-time interpreters. As a conclusion, in this study, we proposed a predictive and prescriptive analytical model to schedule interpreters efficiently. And our model outperformed the current system in the hospital. And then this model, but we didn't have a chance to implement it because I left and there are a lot of barriers to implement the model. But this model can be automated and implemented to generate the schedule of interpreters automatically. And we published this work in Healthcare Management Science. Here's the reference. And then here are the references that we use. And any question? So we finished too early. Any question? Sure.
So thanks, Aziz. I mean, it's impressive. It's amazing. So I got a chance to see you speak. Wasn't that long ago about applying just similar methods or other methods to the challenge of triage in the emergency department, and just kind of the idea of at the point of care and using machine learning. And so I'm just wondering, in terms of opportunities, like these methods seem so powerful in terms of informing things in the health system. Are there opportunities as questions emerge to engage with people like you and who else that have this skill set to kind of address some of the questions that are coming up at the front lines? I'm asking this very selfishly as we just, are working on Learning Health System Month and Learning Health System. A lot of our clinical and operations colleagues have challenges, and I think the different methods and expertise you have could be so powerful in helping address some of their pain points in the health system.
The presentation that I did last semester was applying the predictive analytics, and then this part applying prescriptive analytics. So the combination of both areas. There are a lot of applications, and they're very powerful methods to optimize system. You can imagine Amazon relies in both predictive analytics and prescriptive analytics to optimize all their operations. In a hospital, there are a lot of hospitals use those methods for capacity planning and bid assignments, and so yeah, there are a lot of opportunities to apply these methods in the health system. In fact, I am working with Stu, and we're trying to develop a predictive model or a deep learning model to predict how many patients in the waiting area at emergency department every 6 hours, so they can inform the inpatient unit to activate different capacity. They call it capacity level, not capacity level. Something protocol. They activate different protocol to maybe discharge, early morning discharge, or different protocol that they use in the hospital. And then we're trying to expand this and use also prescriptive analytics to do capacity planning as well. So yeah, there are a lot of applications and opportunities.
Yeah, no, thank you. I mean, they're just wonderful tools in the toolkit, and the predictive and prescriptive, and I'm sure you have other tools in the toolkit that really could be brought to bear to address some of the real challenges that we face in the health system day to day. So thank you for sharing.
Sure.
Other questions?
This is Madeline. Hi, can you hear me?
Yes.
Hey, yes. I mean, do you think there's room for this type of work to help predict and or address COVID waves and surges? Because I feel like, is there any way to extrapolate from population case counts and things into the expectations into the hospital system? Has that been, maybe that has been done?
So when you said COVID, in terms of what? In terms of language, or like helping
your modeling,
Yes.
just your modeling, and how you were saying your work with I think Dr. Cohen in the health system at UAB.
Yeah. Of course, you see those methods, either predictive analytics and prescriptive analytics, are universal and can be applied in any application area and any problem, as long as we use the right data and we ask the right questions and we formulate the problem. Because the hardest part of these applications is to formulate the problem. Once we formulate the problem, yeah, of course, we can apply it, and then, and of course, there are powerful methods that can improve systems. And yeah, give you another example of COVID. Alison and I and Rian, Farhat, and we were working on a data with the hospital system to develop a model to predict the ICU versus non-ICU patient at the point of admission. Like once the patient, like the first 10, 15, 20 minutes, the patient arrived to the emergency, so we can predict whether a patient will be admitted to ICU or not, using patient history and vital signs and demographic and all the historical data. And we were able to develop a model with accuracy of the highest accuracy model was 82%, which is much better than nothing or guessing.
For sure. Can you share some of what those predicting variables were? Is
Yeah.
that shareable?
Of course, yeah. The vital signs, and then demographic, and if the patient readmitted or not, if the patient is put in nasal cannula, and patient has heroin history or drug history, and yeah, there are we had about 100 predictors, and then we were able to narrow them down because there were a lot of missing values and this and that. We narrowed them down to, I think, 35 predictors. And then from the 35 predictor, we were able to narrow them to only 10 predictors to predict the ICU versus ICU patient. And we're working on the paper. It will be out soon.
No, that's great.
Yeah, thank you.
Yeah, no, it's really great. I'm also curious because, gosh, years and years ago, when I first joined faculty, a lot of years ago, I remember Jerome Allison, was here for many years and talked about the difference between explanatory and predictive modeling. And kind of the way he broke it down, just simplifying, was, with explanatory modeling, you're really focusing on what is the parameter estimate for each of these individual components. Whereas with predictive modeling, a lot of times it's more about how does the sum of these different predictors that go in the model have some degree of precision, whether it's AUC, and something of that nature. So, and I guess insofar as the parameter estimates, it's more if you want to do a weighted score. So if you want to say, okay, these different things, but does that still hold true? The idea for predictive modeling, a lot of times the concern is less about the weight of each parameter estimate, but how does this combination of 35 or 10 variables ultimately predict this outcome of interest?
In the past, machine learning was like black box, like neural network and boosting algorithms, black box. You feed them with data and then you do the prediction, but you don't know the effect of each variable. Is it positive or negative, or how much is the effect? But now with the whole research area of explainable machine learning, so there are lots of tools that can be used to visualize the effect of black box variables. So I just submitted a paper and we used a black box model. It was XGBoost, but there is this package, you can Google it. It's called SHAP, SHAB, and it's used to explain all these variables, the effect, the amount of effect, and the direction of the effect. So now it's become open box, and you can see everything, like the effect and the amount and the direction and everything.
Yeah, No, thank you. I mean, it becomes important just thinking about interventions and programs, right? So, I mean, because then if you just can predict something, then you know the outcome. But if you understand what factors are leading to that outcome and the relative weights and directions, and if they're modifiable, now we have targets, whether it's, it's at a system level, individual level. So the idea of to both predict accurately, but also have a sense of what variables and their relative effects. I mean, I think in terms of designing interventions, so that really resonates with me.
Yeah.
And there's a question in the chat from Bing.
Software. And then for
technical questions. That's great.
Yeah, for the software, we used Groovy Solver. It's a company that developed the software for optimization. And then the environment type is Python to code and to use that software. There is also Cplex, if you're interested, developed by IBM, and there are other solvers, but we use Groovy. And then the second part of the question, the parameter tuning, the challenge regarding calibration across foundation. Yeah, for the calibration, that's the hardest part of developing a machine learning model. So you can imagine we run lots of experiments until we get an acceptable accuracy. So yeah, that part took a lot of time to be able to develop an acceptable model.
So Aziz, really want to thank you. I suspect like Stu Booth and others, probably going to have a lot of clinical collaborators knocking on your door. So I hope it's okay.
I also
really helps. Yeah, I think there'll be a lot of people really interested in collaborating with you and applying some of these really powerful methods to different in the health system. So really appreciate you taking the time to share with us. It's amazing work. So thank you for sharing.
Thank you so much. And I saved you guys like 20 minutes so you can have lunch.
Sounds great. Thanks, Aziz. Take care.
Thank you.
Bye. Thanks for joining, everyone.